Hello, Dr. Tracy. This is the final project for COMPSCI3-44024, and this is Group 2's presentation on how your computer works. The contributors to this presentation are Julio, James, Mohammed, and Hannah. The content is separated into 5 sections in the order of CPU diagram, fetch, decode, execute, logic gates and circuits, memory hierarchy, and machine language examples.
Basic computer function from input to output. This is the basic functions of a computer, specifically the CPU.
Input unit. The input unit is responsible for taking data and instructions from the outside world, such as a keyboard, mouse, or sensor, and sending it to the CPU for processing. It converts human-readable input, like letters or numbers, into machine-readable binary format, zeros and ones. Example: when you type a number into a calculator program, the input unit sends that number to the CPU to be processed. CPU Central Processing Unit. This is the brain of the computer, where all the actual processing happens. Inside the CPU, there are 3 key components that work together. Control Unit, CU. The control unit manages and coordinates all the CPU activities. It doesn't perform calculations itself. Instead, it tells the other parts what to do. It fetches instructions from memory, decodes them, and sends control signals to the ALU and memory unit. Example: if the instruction is add 5 and 2, the control unit tells the memory unit fetch the numbers 5 and 2. The ALU to perform addition. The output unit will display the result. Memory unit, also called primary memory or main memory, RAM. It stores data, such as numbers, text, inputs. Instructions is program code. And intermediate results, temporary data during processing. The control unit reads the instructions from memory one by one and executes them. For example, when you run your MIPS code, your array and loop variables, $T0, $T1, etc. Those are stored in memory. The ALU, Arithmetic and Logic Unit. The ALU performs all arithmetic operations, addition, subtraction, multiplication, and division. The logic operations, comparisons like equal to, greater than, or less than. It is where all real computations happen inside the CPU. Example: if the instruction says square 3, the ALU performs 3 multiplied by 3, which will equal 9. Output unit. Once the CPU finishes processing, the output unit sends the results to a device humans can read or use, like a monitor, printer, or speaker. It converts binary machine data back into human readable form. Example: in your MIPS lab, the output array with squared numbers stored in memory is later shown as a result in the ZY-Books simulator. That's the output unit's role conceptually. Next, we'll talk about fetch, decode, and execute. Fetch. The CPU goes to memory and fetches that next instruction. It uses the program counter, PC, to know where that instruction is stored. Decode. The CPU sends the instructions to the control unit, which decodes the binary pattern. This tells the CPU what operation to perform. Example: load, add, store, and which registers or memory addresses to use. Execute. The CPU carries out the instruction. For example, if it is an add ADD, or add ADI, the ALU adds 2 registered values. If it's a load, LW, data is copied from memory into a register. If it's a store, SW, Data is copied from a register to a memory.
Logic gates basic combinational circuits. Like binary gates are controlled with zeros and ones. The transistor tells the circuit to 1 allow or 0 don't allow to write to memory. Let's start with the basics. This little guy right here will do. This is the basic and gate. 1 allows system to write to memory, whereas 0 does not allow system to write. As you can see in the tables, all gates follow this rule. As illustrated right here and here and here. Time diagram works with the clock. This will correlate with the logic gate. As you see in this example, the timing will rise to 1 when input is allowed, then return to 0 when writing is not allowed. This timing speed is the clock portion of processing. When all line up, they can be written to memory.
The memory hierarchy of a computer contains many different levels of memory, with the registers and caches being in the kilobytes and megabytes. Then there is the random access memory, which is going to be in the gigabytes, and then the storage, which is going to be in the terabytes. Cache is memory that is fast and located on the CPU chip, and it's used to store frequently accessed data, which is going to provide lower latency since it's on the actual CPU chip. And there are different levels, with L1 being the smallest but fastest, and L3 being the larger but slowest. And registers are very similar to the caches in that they're very small and fast, but registers are used by the arithmetic logic unit to store values that it's currently processing. RAM is further away from the CPU chip, so there's latency. So it's going to be slower than the cache or registers, but it's going to be quicker than the storage. RAM and the caches are both volatile, which means they lose their data when power is removed. Storage, on the hand, is non-volatile. It means the data is retained. So storage is used for long-term storage, and the RAM is used to store data that is currently being processed, since it's quicker than storage. When a program is executed, it's not practical to run the program from storage since it's so slow compared to the RAM and caches. So the program is copied from storage to the RAM. RAM operates much quicker, experiences less latency since it's closer to the CPU. As the CPU continues to process data, any frequently accessed data is saved from RAM to the caches since the caches are much faster. The CPU will first check the caches for the data it needs. If it's located there, it's considered a hit, reducing the number of CPU cycles needed and improving performance. The ALU in the CPU will use the registers to temporarily store data that it's using in its calculations, since the registers and caches are located in closer proximity on the actual CPU chip than RAM and storage.
So machine learning is basically the raw instructions the CPU actually works with. It's all ones and zeros, and that's how the computer understands what to do. Any code we write, like C or Python or whatever it is, eventually gets turned into that. Machine learning tells the CPU things like load this number, add these values, or store this result. It's the most basic level everything runs on. So here I'm just showing a really simple example of how machine language looks. On the left side is the assembly code, which is the human readable version, kind of. And then on the right side is the same thing, but in binary, which is what the CPU actually works with. Each instruction gets turned into these ones and zeros, and then the CPU fetches it, decodes it, and runs it. This is basically what's happening behind the scenes every time your computer does anything. So this example, I'm just showing how a small piece of C code turns into IMPS assembly. And then finally, machine code. The C code sets X to 7 and then adds 3 to it. On the right, you can see the IMPS version, which is what the computer understands, but at a slightly higher level. And then underneath is the machine code, which is the binary form the CPU actually runs. This is basically the full process of how a simple instruction gets turned into ones and zeros.
In summary, the CPU is a combination of different components, such as the control unit. The fetch, decode, execute cycle is an overview of how the CPU fetches, decodes, and executes instructions. Logic gates take binary inputs and output a single binary number and use in operations such as arithmetic calculations. The memory hierarchy contains different speeds and sizes of memory depending on the purpose of the process being executed. Machine language is the binary instructions the CPU executes. This was Group 2's COMPSCI3 44024 presentation on how a computer works. Thank you.